So again, thank you all for coming to our July public lecture. Welcome to the U.S. Geological Survey. I'm William Seelake. I'm with Science Information Services here in Menlo Park. And that's probably a little better. There we go. Quick reminder before we get started. Our August lecture next month will be held on the 31st. The title is, the subject is Mars Rover Curiosity's Exploration of Gale Crater. You can pick up a flyer on the back table over there. Tonight's lecture is titled Warm Ice, the Dynamics of Rapidly Changing Glaciers, presented by USGS's Bruce Molyneux. So a little bit about Bruce. Bruce is he's a PhD, and he is served as the USGS Senior Advisor for the National Civil Applications Unit, and is also an award-winning research geologist. He's conducted glacial, marine, and coastal research for over 50 years. His current activities focus on innovative uses of remote sensing, the response of glaciers in Alaska to changing climate, presenting understandable science to the public, policymakers, and the media. Mr. Molyneux, who has been awarded the DOI Meritorious Service Award, the USGS Lifetime Communications Achievement Award, and the Geological Society of America's Career Achievement and Public Service Awards, as well as 3 USGS External Communication Awards. He has authored more than 350 articles, abstracts, books, and maps, mostly focused on the Alaskan region. Dr. Molyneux has worked for the USGS in Menlo Park from the years 1974 to 1983. So again, please give a warm welcome to Bruce. And please hold all questions until after the lecture. Thank you.
Good evening. How are you? So, as you've heard, my name is Bruce Molyneux. I am a research geologist and have spent more than 40 years working for the U.S. Geological Survey. And my focus has been on trying to understand the dynamics of rapidly changing glaciers. And what I'm going to do is make a presentation that has 3 components. First part I call Glacier Numerology. It's the how big, how long, how thick, how much, how often, about basic glacier information. Then we'll talk about Glacier Photography, focused on Alaska, and we'll look and see what imagery can tell us about the dynamics of Alaskan glaciers. And then finally, I'm going to describe a research project that I've been involved with for quite a number of years. And it's one that is focused on the use of geophysics. And what's remarkable is about every decade a new technology evolves. And each new technology allows us to get new insights into addressing a problem that we started to try to understand in the mid-1970s. A lot of what I'm going to say is already in print in a USGS professional paper that came out about a decade ago, the Alaska chapter of the Satellite Image Atlas of the Glaciers of the World. And a lot of this numerology, especially related to sea level change, is on a website that I have, and you can see the URL of the website at the bottom. On this website, the professional paper is also available, and you can download it or just look at it online. So some basic definitions. Let's begin with a glacier. Glacier is, by definition, larger than a square kilometer, or about 4/10 of a mile. It's a perennial accumulation of ice and snow, rock, sediment, liquid water, originates on land, and moves downslope under the influence of its own weight and gravity. Glaciers form from the metamorphism, the recrystallization, of snow into hexagonal glacier crystals, ice crystals. And glacier ice has a density of 0.91. Liquid water has a density of 1.0. That's why icebergs float with 90% of the iceberg submerged. An ice sheet is a large mass of glacier ice, typically with areas greater than 50,000 square kilometers, 20,000 square miles. And today, ice sheets cover most of Greenland, and there are two in Antarctica, the large West Antarctic and East Antarctic ice sheets. During the last ice age, the Pleistocene, ice sheets also covered large parts of North America and Scandinavia. An ice shelf is a permanent floating sheet of ice that connects to a landmass. They form where glaciers actually leave the terrestrial environment and move into the ocean, and because of the density of the ice, it floats. Around Antarctica, where there are more than 40 of these ice shelves, the topography or the bathymetry of the continental margin is extremely different from what we're used to here on the west coast or the east coast of the United States. There, it is extremely deep at the shoreline. You go offshore and you're already in 400 or 500 meters of water in many places. So these large masses of glacier ice leave the continent and float out into the Antarctic oceans. Antarctica has, as I said, more than 40 of these, and one, the Larsen Sea Ice Shelf, has gotten quite a bit of attention in the last few weeks as a part of it that represented about a trillion metric tons of ice broke off and is now known as iceberg B68. So let's get into the glacier numerology. I titled my talk Warm Ice, and you might want to know the difference between warm ice and cold ice. Warm ice is the ice that we find in most Alaskan European temperate glaciers, and the temperature of the ice is within a very small fraction of the degree of the melting point. So in terms of Fahrenheit, a typical glacier will have liquid water in contact with the ice crystals, and the temperature of the ice at the surface may be only about 1/10 of a degree below the freezing point. At the South Pole, if you were to measure the temperature of the ice at the surface, it's minus 50 degrees Fahrenheit, about minus 45 degrees Celsius. So there's a significant difference between the behavior of warm and cold ice. Warm ice flows very plastically, deforms without fracturing. Cold ice is very brittle and shears. So we're talking today, for the most part, about the dynamics of Alaskan glaciers, which are warm ice. But to go back to the South Pole environment, there you've got 2,800 meters of ice. You've got 9,000 plus feet of ice. And the temperature at the surface, about minus 50 Fahrenheit. Temperature at the bottom, about plus 15 degrees. It's only about 20 degrees below the freezing point. But in the middle of the that 9,000 foot thickness of ice, the ice temperatures may be minus 40 degrees Fahrenheit. So there's a very, very significant difference between warm ice and cold ice. And warm ice, just because of the fact that it is so close to the melting point, is extremely susceptible to rapid melting when you get temperature increases, as we've been experiencing in the last century. The number of glaciers on Earth, about 200,000. These are glaciers larger than 1 square kilometer. If you count all of the sub-square kilometer glacierettes, the number goes up to about 450,000. This number does not include the big ice sheets. When did glaciers first appear? Well, the evidence in the geological record goes back 2,900,000,000 years ago. So glaciers are not a modern phenomenon. They've been around for at least half the age of the Earth. And if you look at the geological record, you can find evidence of more than 100 major continental glaciations that are preserved in the rock record. If there were only 1,000 drops of water on Earth, and they represented all of the water, what we would discover is that 972%, or 972 of those drops, 97.2%, are in oceans and inland seas. 21 would be in glaciers. 6 would be in groundwater and soil moisture, and less than 1 in the atmosphere, less than 1 in all the lakes and rivers on Earth, and less than 1 in all the living plants and animals on Earth. So, although probably very few of you were aware of it, Glaciers are the single largest repository of fresh water on Earth. So 97.2% salt water, 2.8% fresh water, 2.1% of that 2.8% glacier ice. If there were 1,000 ice crystals, and that represented all of the glacier ice on Earth, we discover that 914 of them are in Antarctica, 79 in Greenland, approximately 4 in North America, with more than 3 of them in the Canadian Arctic, approximately 2 in Asia, and less than 1 in South America, Europe, Africa, New Zealand, and the island of Irian Jaya, which is New Guinea and Indonesia. So 99.3% of the glacier ice on Earth is polar in Greenland and Antarctica, and 0.7% is temperate glacier ice. How much ice is there on planet Earth? About 16,434,000 square kilometers, of which 14 million are in Antarctica, 1.7 million in Greenland, and all of the others on Earth only about a little bit more, approximately 750,000 square kilometers. So Antarctica, without question, the greatest concentration of glacier ice on Earth. Last time that Antarctica's ice cover melted completely away, approximately 20 million years ago. Last time Greenland was ice-free, about 110,000 years ago. 110,000 years ago, sea level was about 20 feet higher than it is today. And at that point in time, the fall line, which is a feature on the East Coast, at the inner edge of the coastal plain, was formed. And the fall line is a major erosional scarp that marks the extent of the Atlantic Ocean 110,000 years ago. Glaciers exist on 6 continents. The only continent without glacier ice is Australia, although in the geological record of Australia, there are several geological units that contain glacier-transported rocks going back, in this case, about 350 million years ago. In Alaska, there are 14 different regions that support glacier ice. And what most people don't realize, almost all of the glacier ice in Alaska is along the southern coast of Alaska. The southern coast and in the Alaska Range. Alaska Range is this area here. Once you get north of the Alaska Range, you're moving into a subpolar desert. And so the existence of glaciers in Alaska is concentrated around the Pacific Ocean because it's the Pacific Ocean moisture source and the presence of very high mountains that contribute to the formation of the glaciers of southern Alaska. There's a period of time from about 1250 AD to 1900 AD called the Little Ice Age. And during the Little Ice Age, glaciers on the 6 continents that currently support them expanded dramatically. Winter temperatures were as much as 4 degrees Fahrenheit, 2.8 degrees C, lower than they were today. And the coldest part of the Little Ice Age was the second half of the 17th century and the early part of the 18th century. During that period of time, most of the larger glaciers in Alaska expanded to what we call their Little Ice Age maximum positions. And they've been retreating in many, many places, in some cases for the last 250 years. Total amount of glacier ice in Alaska today is about 86,000 square kilometers. It's about 33,000 square miles. There are 26,000 glaciers in Alaska larger than a square kilometer. Of that, about 2,000 are large valley glaciers. And of those 2,000 large valley glaciers, only about 700 have names. So 2/3 of the glaciers in Alaska, the large glaciers in Alaska, are unnamed. The biggest glaciers in Alaska, the Bering and the Malaspina, are complex glacier systems with many tributaries and complex Piedmont lobe termini. And those 2 glaciers each are about 5,000 square kilometers. Those 2 glacier systems are each about 5,000 square kilometers in area. Today, of all the valley glaciers in Alaska, more than 99% are currently retreating, thinning, or stagnating, and most notably you see this at the lower elevations. There are many places where lower elevation glaciers have completely disappeared during the 20th and 21st centuries. However, just to make things more complicated, there are a handful of Alaskan glaciers that are currently advancing. And we can talk about why that's happening a little bit later. Temperatures in Alaska are very interesting. This is a map showing the location of the 19 first-order U.S. National Weather Service weather stations. And if you look at the average temperatures, you can see that between 1949, when the weather stations were established, and 2016, the mean seasonal annual temperatures in Alaska have increased by more than 3.5 degrees Fahrenheit. But also, if you look at the seasons, you see that the single greatest increase in temperature has been in winter. So winters in Alaska are warming. Last year was an abnormally warm year in Alaska, and the average temperature last year was more than 6 degrees Fahrenheit warmer than the moving average of temperatures since the 1940s. If you look at these three diagrams on the right-hand side, you can see that pre-1970, Alaskan temperatures were significantly colder than the long-term norm. And then in the mid-70s, temperatures dramatically increased. And this is due to a shift in atmospheric circulation of something called the Pacific Decadal Oscillation. When it moves northerly, it brings warmer, wetter ocean air over Alaska, and temperatures warm. When it moves southerly, it allows much colder Arctic air to cover most of the surface of Alaska. And so even though it's called a decadal oscillation, it actually seems to have a duration of many decades, 40 or 50 years at least. But if you also look at the diagram in the upper right, you can see that the last few years have been significantly warmer than any of the other years in the post-World War II time period. So, what does that mean for glaciers? And this is a good example. This glacier, located in the Chugach Mountains, is rapidly melting to the point where these linear stripes of sediment, which are called moraines, are actually elevated above the surface of the rapidly thinning ice. But there are a number of other telltale signs in this picture that allows someone with a knowledge of glacial geology to determine what this glacier has been doing. The height of the vegetation on the side here shows that the ice probably was as thick as where the cursor is in the not too distant past. And all of this sediment stranded on the other valley wall here. This is the lateral moraine that was the sediment trapped between the edge of the ice and the bedrock wall here. So this is a cirque glacier. You can see several of its source cirques up here, and the ice is rapidly melting away. And so where is that water going? It's going into the oceans. So global sea level is rising for two reasons. One, we're adding more molecules of water, and two, the temperature of those molecules is increasing, and water molecules expand as they get warmer. So that's called steric sea levels change. So the addition of more molecules and the enlarging of the existing molecules is causing sea level to rise. How much did it rise in the last century, in the 20th century? And these are based on tide gauges, anywhere from 12 to 22 centimeters, depending on where you were measuring. So that's between 5 and about 9 inches. However, not all coastlines are experiencing sea level rise. There are many places on Earth, especially along the west coast, where tectonics is actually elevating the land surface more rapidly than sea level is rising. So if you go to Juneau, sea level is falling about 2 inches a year. The Intergovernmental Panel on Climate Change estimates that by the year 2100, the global average sea level will rise anywhere from 18 to 59 centimeters, between 7 and 23 inches. And this is a diagram from the IPCC report. It shows that from the 1800 time period to 1900, there wasn't any significant change in sea level. The light red is the tidal gauge record. The green is the satellite record of sea level change. And the blue is their prediction of what sea level might do over the next century. About 20,000 years ago, global sea level was about 125 meters lower than it is today, more than 400 feet lower than it is today. So if you were on the East Coast and you were standing at the current shoreline, everything that you could see off to the east would be exposed land surface. The edge of the ocean was 60 to 80 miles further to the east back 20,000 years ago than it is today. And then about 8% of the Earth's surface was covered by glaciers, 25% of the Earth's land area, and about a third of Alaska. Excuse me. Today, only about 3% of the Earth's surface is covered by glacier ice. That's 10% of the Earth's land area, and only about 5% of Alaska is covered by glaciers. Between 18,000 years ago, when sea level began to rise, and about 6,000 years ago, when it stabilized at a level close to what it is today, the oceans rose more than 125 meters. And so when you do the math, that's about a meter per 100 years, which is comparable to the prognostication of the IPCC as to what we might encounter in the next century. And then the last piece of information here in terms of glacier numerology is, as I mentioned before, the Larsen C ice shelf had a 5,800 kilometer piece break off between July 10th and 12th, and represented 12% of the total area of the Larsen C ice shelf. And what we've been seeing over the last 50 years are what is referred to as a collapse of ice shelves around Antarctica, with significant amounts of calving taking place, and large icebergs, some of which are hundreds of kilometers in size, breaking off. And a lot of this is due to the fact that the temperature of the Antarctic Ocean is warming, and this warmer ocean water is able to penetrate from the bed of the glacier, the floating glacier ice, get into cracks, and cause the rapid deterioration and breakup of the ice shelves. So let's talk about glacier photography. The first known photograph of an Alaskan glacier was in 1883. By 1920, mostly through the efforts of USGS geologists who were surveying the mineral resources of Alaska, more than 400 glaciers were photographed. By 1929, the first aerial survey of glaciers took place in southeastern Alaska, and all the glaciers were photographed from the air. By 1960, all of the glaciers in Alaska were photographed from the air, mostly by the Navy and the Air Force. Also in the 1960s, DoD space-based satellites began imaging Alaskan glaciers. And in some of the imagery that's been declassified and made publicly available, there are amazing photographs of glaciers in the 1960s and 70s taken by the early Corona and Keyhole satellites. Beginning in 1972, the Landsat satellite began to systematically observe glaciers of Alaska. And now, some of the glaciers in Alaska have been imaged more than 1,000 times. And in 1976, the first space-based radar imagery of an Alaskan glacier was made. So this is the first known photograph of an Alaskan glacier. This is the, quote, Muir Glacier, located in Glacier Bay. Photograph was made in 1883. John Muir discovered, quote unquote, discovered Glacier Bay in 1879, and within 4 years, tourism was extremely prevalent. There were cruise ships coming up from both Bellingham, Washington, and Tacoma, bringing tourists with cameras to Glacier Bay, and there are numerous photographs, pre-1900 photographs of Alaska, taken by these tourists who came up to explore the Muir Glacier. Now, even though John Muir, quote, discovered Glacier Bay in 1879, the local inhabitants had been living there for about 4,000 years. So let me point out this feature that you see here, this bedrock mass shows up in many of the early photographs, and it's an important feature because it allows us to locate the terminus of the glacier in the early 1880s and look at how it's changed over time. So this is an 1899 photograph by a USGS geologist named Grove Carl Gilbert, and if you just watch what happens, you can see how the landscape has changed over a 103-year time period. And so we went from the terminus of Muir Glacier pretty much filling the entire foreground to glaciers being long gone, and the closest glacier ice is about 30 miles away in the very right-hand side of the image. The other thing that's important to note, even though this is a black and white image, if it had been in color, it would still pretty much be black rock and white ice. And so we have this progression from black and white to blue and green. And so vegetation is established very, very rapidly. And you'll see in some cases it's so rapid that it's mind-boggling. Most of the literature suggests that ecological succession takes several hundred years to go from bare bedrock to a forest. In many places in Glacier Bay and other southern coast of Alaska locations, we have forests being established in less than 50 years. So let's take a look at some of the different types of photography that allow us to understand glacier dynamics. This is a 1926 photograph from the U.S. Navy U.S. Geological Survey Joint Photographic Reconnaissance Mission. And what's interesting, the mission consisted of 4 biplanes. You can see 3 of them here. The 4th one is taking the picture. And there were 2 cameras in the biplanes. One was a vertical camera through a hole in the bottom. The other was a handheld camera weighing 60 pounds that was located in the back of the plane. So there was a pilot in the front seat, there was a photographer in the back seat, and the photographer was taking oblique photographs over the side of the open cockpit. And collectively, these 4 aircraft between 1926 and 1929 collected about 40,000 photographs of southeastern Alaska. So all the glaciers in Glacier Bay were well photographed by the 1929. Brad Washburn took this picture of the Harvard Glacier, which is one of the few advancing glaciers. This is 1938. Satellite imagery gives us a much more reliable source of imagery about which we can then make determinations of how glaciers are changing. So this is a map showing the locations where Landsat images are. Landsat is a satellite that repeats its orbit every 7 or 8 days. And so each of these areas that's in light purple is a location of a scene that has glaciers in it. And so the way the Landsat satellite orbits, it repeats taking images over each of these scene centers. And since Landsat first was established in 1972, as I said, many of these glaciers were imaged more than 500 times and some more than 1,000 times. So what can we see? Here's an example of the Juneau ice field in a 1984 Landsat image. And then here's a sequence of 4 images that NASA put together showing the rapid retreat of the Columbia Glacier. Here's its terminus in the lower part of the center of the image. This is 1986. It retreated about 8 miles by 1985. Retreated another 6 miles by 2008. And then separated into its main branch and its west branch by 2011. And so Landsat is a very good way of looking at large area change. Landsat, unfortunately, is based on what we call pixels, which are individual reflections from the Earth's surface that are 15 to 30 meters in size. High-resolution photography has pixels that are less than a meter. In fact, many of them are less than a foot in size. So if you really are looking at detailed change, you need to have a much more highly focused, more resolution type of an image data set than Landsat. But for synoptic regional change, Landsat is an excellent tool. So let's look at a group of individual photographs, and this is what I call a photographic forensic analysis, trying to determine what changes have occurred. And we'll begin with this photo of a glacier in the Chugach Mountains. That each of these is a cirque, and these are remnant cirque glaciers. At one time, the ice filled each of the cirques and contributed to a much larger glacier that moved down valley and off the bottom of the image. But during the 20th century, and here we're at an elevation of about 6,000 feet, a little bit less than 2,000 meters, there's been this dramatic melting, and you can see all of the sediment that's been left behind the different types of moraines. This is a glacier called the Tana Glacier, and in the 1950s, the Tana Glacier made contact with this valley wall that the cursor is moving along, and the trim line, as this is called, shows you the height of the ice. By 2000, the glacier was stagnant, melting away in place. You can see all these icebergs that are breaking off of it, and vegetation is becoming established, typical of a warming environment. This is part of the terminus of the Malaspina Glacier. This is glacier ice from this carpet of vegetation here down and below the surface of the water. And these are trees, Sitka spruce, mountain hemlock, some cottonwood, and some alder, that in many cases are as much as 200 years old, growing on the surface of the stagnant glacier. There are as many as a dozen glaciers along the southern coast of Alaska that support forests on stagnant ice. This is the Lituya Glacier, shown here, in Lituya Bay in Glacier Bay National Park. And there's a really interesting story here. This line going across the valley wall here is known as Solomon's Railroad. And that is the top of the lateral moraine, showing how thick the ice was in the 16th century. It was about 500 meters higher than the elevation of the bay. This line is a scar from a huge landslide that took place over here. This massive rock, million cubic meters of rock, fell into the fjord, caused a splash wave, then went up 1,754 feet and stripped all the vegetation off the side of the valley. And this is the vegetation that's become reestablished since that earthquake-induced landslide in 1954. What makes it even more interesting, there were 4 fishing boats anchored at the mouth of the bay that were transported up and over the moraine at the mouth of the bay as much as 4 miles into the Gulf of Alaska, and there were survivors on 2 of the boats. So they're eyewitness stories. And that's just one example of some of the unusual types of dynamics that can occur in a tectonically active area with glaciers. Another glacier, here's the ice terminus. This large moraine shows how big the glacier had been during its little ice age maximum. This is melting rapidly, and you can see how quickly the vegetation gets established in the area that the glacier ice has vacated. Okay, it's the last of the single photographs. This is a bay in front of the Neliwan Glacier. This is Neliwan in Prince William Sound, western Prince William Sound. The star here is a photographic site location, and the next pair of images I'm going to show you were taken from that location, looking across the bay here from this point in this direction. So the first image was taken in 1909, and you can see the extent of Neliwan Glacier. This is close to the edge of that bright blue bay that we saw in the last photograph. And then this is the same location in 2011. And here are the pair of images. So we went from this large Tidewater terminus of a glacier to the complete retreat out of the field of view of Neliwan Glacier in a period of 102 years. This is a 1957 photograph looking towards the terminus of the glacier. And this is a 2011 reef photograph of the same area. And so we went from glacier sediment, Glacier Bay, and bare ice, to the complete disappearance of the glacier ice, and a coastal wetland, a marsh, and mature trees, all in the space of less than 60 years. I mentioned Harvard was one of the advancing glaciers. It's hard to see in this pair of images, but this is 1938, this is 2006, but you can see it more clearly in a ground-based pair of pictures that I'll show you next. So this is Harvard in 1909, and this glacier here is called Baltimore Glacier, and you can see its extent. This is Harvard, and this is the tributary coming in, this is Radcliffe. Seriously. Here is the same location in 2002, so we're looking at about 93 years of difference. Notice Baltimore Glacier is significantly smaller, but Harvard has been advancing dramatically. Pedersen Glacier in the Kenai Fjords, 1909 photograph. Again, bare bedrock, glacier ice. Same location in 2004. But what makes this even more interesting, these trees were drowned when the ground surface submerged in the 1964 earthquake. This area went down about 15 feet. So between 1909, when you had glacier ice, no vegetation, a forest developed, and in less than 55 years, it grew and then was killed by the earthquake, and the area then became a coastal marsh. Columbia Glacier, this is a 1931 photograph. Here's the terminus, and it's pushing a moraine in front of it. And then here we are 80 years later, and there's no ice to be seen anywhere in the photograph. No glacier ice, just some icebergs floating. Rapid change is characterized by this pair of images. This is 2002. This is South Sawyer Glacier, which is in a Tracy Arm south of Juneau. And 7 years later, there was this massive loss of ice. And you can see the trim line again, showing what the height of the ice had been in 2002. This is a photograph that Brad Washburn made in 1938. Shows up in many textbooks. I made an effort to duplicate this one in 2006. And what you can see along the valley wall here is that the ice is thinned, exposing, again, this trim line. But for the most part, looks quite similar. If we had looked the opposite direction, we would have seen that most of the terminus of the glacier had disappeared. Can move from where we were in Prince William Sound to Glacier Bay. Glacier Bay is one of the more unusual, well-documented glacier retreat sequences in Alaska. And about 1750 AD, Glacier Bay was completely filled by a large, massive glacier ice. Within 100 years, the ice retreated about 30 miles, opening up Lower Glacier Bay. And as you can see, there's an east arm and a west arm because the ice is going to continue to retreat and separate. By 1890, the west arm was almost completely exposed, and the east arm was just slowly beginning to emerge. By the 1930s, most of the east arm is visible, and some of the side fjords start to emerge in the 1960s and the 1980s. So what does Glacier Bay look like now? Pretty much this blue mass with huge amounts of vegetation and just a few remnant glaciers, all in the upper parts of the fjords. What we're going to do is look at a sequence of about 7 pairs of photographs to document the rapid retreat of glacier ice in the east arm. We're going to start with this 1886 photograph. And notice the way tourists dressed to visit Glacier Bay in the 1880s. This gentleman with his camera has a formal coat and a top hat. This woman has a bustle and a fur muff. And that's how you went and visited glaciers in the 1880s. What does that place look like in the 21st century? Looks like this. So how do we know? Well, see this rock mass here? There it is. So that's the before and after. So the ice has retreated more than 40 miles from this location since the 1880s. In fact, as this diagram shows, here's where the ice was in the 1860s, the 1890s, and the glacier now is way up here, and we'll take a look at it in a couple of later slides. 1892 photograph, 2005. This is one of the more fascinating pairs that's going to come up. In 1961, this is the side inlet on the west side of Muir Inlet called Wachusett Inlet. This is Plateau Glacier. Notice the two people standing over here on the peninsula. Also, there's no vegetation to be seen anywhere. This is 1961. 43 years later, it looks like this. Remember the people over here? My two field assistants are down here in their orange float coats. They couldn't get there because the vegetation was so dense. So we go from this black and white ice and bare bedrock environment to this extremely well vegetated, almost complete absence of ice. This is a September picture, so the cottonwoods here are already changing color. Continuing along as we move north in the east arm, this is a photograph I took in 1980. I started working in Glacier Bay in 1974. And this is the terminus of McBride Glacier. What did it look like just 24 years later? 23 years later? What does it look like now? So this is where it was in 1980. This is where it was in the 2003 photograph. And here's where it retreated by 2009 when this picture was taken. I was fortunate to be able to get back there 2 summers ago, and I took this picture. And between 2009 and 2015, it retreated another 350 to 400 meters. The next pair of photographs is one of the most reprinted of all of the glacier photographs I've ever taken. Bill Field made this photo in 1941, and I was able to get back to this location in 2004. There are 2,300 feet vertical thickness of ice here. Now there's 800 feet of water. And so notice, in 1941, no vegetation, bedrock, and some tightly compacted glacier till. In 2004, dense vegetation. In his notes, Bill Field wrote, it's about a 15-minute walk up the side of this ridge to get to the photo point. It took us more than 6 hours because we were pushing through the alder. We had no view of the sky. And if we didn't have GPS, we would still be looking for this location. So here's where the terminus of the picture was, the terminus of the glacier was when Bill Field's picture was taken in 1941. By 1950, it retreated here. By 2004, it was another 6 miles off to the left. This is a 1976 photograph I made of the terminus of Muir Glacier. And what's really interesting to me, see the algae on these two lighter bands of igneous rock? These are aplite dikes. they're intruded into this darker bedrock. The glacier was calving so often that the splash waves kept this rock wet. And at the temperatures that were present, the marine algae could grow about 6 or 7 meters above the water surface. In 2003, the glacier is long gone, and the algae is long gone as well, because there is no way it was going to be sustained. It needed the moisture from the splash waves. However, the alder is starting to get established. So 1976, 2003. 1978 photograph. I did not realize when I took this picture in 1978 that there was a 4,000-foot high mountain sitting right here. But when I went back, there it was. So you learn. And I assume this was all clouds. But when you look closely, you can see these jagged, what are called arête ridge peaks in the cloud, in the surface of what is a snow-covered mountain. So this is the retreat of Muir Glacier from being a marine Tidewater glacier onto land. You can see it's out of the water back here, and it's developing large ice blocks that are covered by sediment, stagnant ice. A couple of aerial photographs. A colleague of mine, Austin Post, took this photo in 1986, and I made an effort to duplicate it from the air in 2009, and then again in 2015. And I apologize, I notice I've got the wrong date here, but this is 1986, 2009, 2015. During that period of time, the glacier retreated onto the shoreline about 1994, and it has been continuing to retreat and separate, so the two individual termini are no longer connected. So let's look at that whole sequence. 1941, the ice sat here, began retreating. By 1950, it was here. By the 1970s, it was here. By 1994, it retreated out of the water. 2004, it was down here. 2015, it's back here. Whoops. So I'm going to finish by giving you a short summary of an ongoing project I'm involved with, looking at the Malaspina Glacier, which is the largest Piedmont glacier in continental North America, and the largest Piedmont lobe, which is meaning it's a large, flat, low-relief terminus. It's about 60 kilometers across from east to west, distance of approximately 40 miles. And it's made up of three major tributaries: the Agassiz Glacier, the Seward Glacier, and the Marvine Glacier. Here is the end moraine. This is the coarse component that was deposited by the glacier when it advanced to this point in the early 1800s. And since then, it's been stagnating and wasting away in place, and it's supporting on top of the stagnant ice these 200-year-old trees. USGS expeditions in the 1890s did a lot to map the area. In the 1970s, when I was here in Menlo Park, one of my responsibilities was to collect seismic data in the Gulf of Alaska offshore of the Malaspina Glacier, and from that data we discovered there were deep submarine valleys on the continental shelf. And I was always interested in determining where they went under the glacier. And so this project I'm describing to you is one where new geophysical capabilities allow us, almost on a decadal timescale, to get more insight into what's happening here. Photography shows that the glacier surface has some major sags. And the sags, as it turns out, seem to correspond to places in the bed where there are fjords underlying the ice. So the surface of the glacier topography mimics the morphology of the glacier bed. Here's a Landsat image from the 1972 time period, and you can see how fingers of snow fill some of these depressions, and one of the larger depressions actually corresponds to something that looks like this. A series of Landsat images show that based on the seasonality, the glacier surface looks very, very different. In winter, when it's completely snow-covered, You don't see the complex topography, but as the snow begins to melt, you can get some insights into where these subglacial features are located. This is a radar image that was collected in 1978 of the glacier, and it shows the loop moraines, as they're called, that make up much of the surface of the ice. In 1986, USGS flew its own radar, and we produced an image that looked like this, which is very, very different from what I had thought a standard image of a large Piedmont glacier would look like. And what we discovered is that the surface of the ice, as I had suggested before, was mimicking the morphology of the bed. And so some of these dark areas are the extensions of the fjords that sit out in the Pacific Ocean underlying the glacier, and they extend more than 30 miles up glacier. And in some cases, their depths are as much as 400 meters below sea level. So depths of more than 1,300 feet below sea level. So here's the more traditional radar image and this image that we collected. So we started doing field work in the 1980s to determine what the relief was in these troughs and the adjacent brighter areas. And what we discovered was that these brighter areas, and this is a photograph taken from this point here, and you can see that they're little cirques. This is the floor of the fjord underlying the glacier. And we discovered that there were other places where there were dendritic channels on the surface of the ice, and also one location where we could see part of the plate boundary tectonic fault system exposed as a surface sag in the glacier. When we put our radar image and matched it with the offshore topography, there was a direct linkage between the offshore large channels and the channels that underlie the glacier. In the 1988 time period, we did ice surface geophysics and were able to measure ice thicknesses and depths, and discovered in some places in the distance of 2/3 of a mile, the depth increased by 400 to 500 feet. We wrote a paper basically summarizing what we had found and thought we had been able to answer all of the questions we were asking because we had basically used all the capabilities of the technologies that were available. Then in 2008 and then again in 2012, NASA was testing its Mars ice-penetrating radar, something that they're going to fly to Mars in the future. And we were able to get a number of new transects across the Malaspina Glacier's Piedmont lobe. And when we looked at these, we were able to see the morphology of the bed. Also, we're able to see how the glacier has thinned. These are different surface elevations. This goes back to the 1970s. This is the 2010 surface. And by taking all of these transects, lining them up, and plotting them, what we discovered was there is a distinct correlation between the surface sags on the glacier and these deep fjords underlying the glacier. And that in places, even though the ice is 2/3 of a mile thick, its surface topography mimics the morphology of the bed. And this has shown up time and time again. So 2 years ago, we were able to get back to the surface of the glacier and try a new technology, which is 3D LiDAR. This is a LiDAR. This is a photograph showing one of these moraines on the surface of the glacier, this large glacial erratic sitting here. This is the LiDAR image. So we're able to do a high-resolution topographic map of the surface of the ice from the LiDAR. And now we're doing our first analyses of these data, trying to understand how the local topography manifests itself on different types of radar and photographic imagery, and trying to understand again in more detail the relationship between the surface of the ice and the morphology of the bed. So I'll stop here, and I'll be happy to entertain any questions that you have. I hope that you've gotten an idea that, at least in parts of Alaska, the ice is very dynamic. Certainly, the Larsen Sea in Antarctica is very dynamic. And we're living in an environment in a time when glaciers are changing rapidly, with the major consequence being significant amounts of meltwater making their way into the global ocean and sea level rise becoming a reality that we need to contend with to understand what will happen to places like here in California, the Sacramento River Delta, the Gulf of Mexico on the southern part of the coast, all of the barrier islands on the east coast, and especially in the Pacific, all of the low-lying atolls. So thank you very, very much.
I don't know if you want to use this. Are you comfortable with the mic, or
Sure.
do we want a lapel mic? Or?
No, I'm good.
Oh, okay.
Questions, please. Thank you.
And if you could, make your way to one of the microphones, I have this little lapel mic. This is a good substitute, but yeah, it's easier to line up for the mics for the online audience. Did you have a question?
Yes. I'm amazed I'm going to be the first one to ask a question, but your presentation shows that these glaciers have been melting over the last century, really. What is the difference between the melting then and the melting that we're now concerned about with global warming today?
Okay. It's cumulative. So when it started, we weren't sophisticated enough to recognize that it was having an impact on global sea level. Now, where we can quantify it, because we have so many more satellite capabilities and tidal gauges that have been placed in sensitive areas, we can see the rapidity of the change, and we're seeing that there's actually an acceleration in the rate of melting. You might say, so what? And where the really big so what comes in is that most of Earth's population lives within about 50 miles of the ocean. And most of Earth's infrastructure is within that 50 miles of the ocean. And a lot of that infrastructure is located at elevations that are either at or in some cases below sea level. Case in point, New Orleans. Or I was on vacation 2 weeks ago in the Netherlands, where there are many places that are 20 feet below sea level that are protected by these massive polders, these dikes. And so as global sea level continues to rise, we are faced with a question: do we protect the infrastructure because people are located there? And if we're going to protect it, what's the cost and who's going to pay for it? Now, the last time that there was a major continental glaciation, Earth's inhabitants were much more primitive. As sea level rose and fall, they would move and follow the falling sea level, or they would migrate with the rising sea level. We don't do that anymore. We've got permanent infrastructure all over the place. So most of the retreat in Alaska started in the middle 18th century. In southeastern Alaska, many, many, many glaciers were already beginning to retreat by 1755, 1760. Other parts of Alaska didn't have retreat until later. But as you saw from my numbers, the amount of glacier ice in Alaska and all the temperate locations on Earth is really insignificant. It's Greenland and Antarctica that are critical. If Greenland were to melt, global sea level could go up close to 20 feet. We are seeing more melting in Greenland today than has been observed in previous years. And when I say more, one of the new phenomena in Greenland are these large rivers of blue water flowing off of the perimeter of Greenland into the oceans. And coupled with that is rapid breakup of glaciers, such as the Petermann Glacier, which lost a piece of ice the size of Manhattan 2 years ago. In Antarctica, all of the perimeter outlet glaciers and the ice shelves, many of the ice shelves, are showing breakup and retreat. Now, the ice shelves don't contribute to global sea level because they're already floating on the ocean. It's water that's in the ocean, although it's in solid form. But the glaciers that are rapidly moving into the ocean are contributing ice at a much greater rate. And as the temperatures are increasing and the water is expanding, we're seeing almost an exponential increase in sea level rise in many sensitive areas.
I have a question about the first photo showed northern Alaska had virtually nothing.
Yes.
Zero. And this has been going on for literally hundreds of years. Have there been major weather changes that have caused the retreat, except for the current problems?
Okay.
But going back hundreds of years.
Northern Alaska, almost all the glaciers are in the Brooks Range. Brooks Range has maximum elevations of about 8,000 feet and gets precipitation on the order of 5, 6, 7 inches a year. So it's a polar desert. With warming temperatures, all of the Brooks Range glaciers are rapidly melting, and many of the lower elevation ones have already completely disappeared. The glaciers in the Brooks Range were at their maximum size between the 14th, 15th centuries and the 19th century. And there's been just dramatic retreats since then. Other questions, please.
With the topography you show of the fjords under the Malaspina Glacier, I assume that those fjords were carved by previous glaciers.
Correct.
But they weren't filled with sediment when those glaciers retreated. I mean, they're still there, and why is that? And does that mean that the mountains that are directing the existing glaciers coming into Malaspina have been there all of these years? Or
The mountains-
what's all this say about
Okay.
what's dynamically happening?
Let's talk about the chronology. The tectonics that created the coast mountains probably started 10 million years ago, plus or minus. So there's been high topography along the southern coast of Alaska for 6, 7, 8 million years. The oldest glacier, the evidence of the oldest glaciers along the Gulf of Alaska coast is between 2 and 3 million years back in time. That's based on the sediments in the Gulf of Alaska that have been cored. Glaciers deposit sediment underneath them while they advance and retreat. When glaciers melt, the significant increase in the availability of meltwater flushes a lot of that sediment out from the fjords into the adjacent ocean. There's probably a lot of remnant sediment under the ice, but the bedrock, which has been probably eroded over millions of years, maintains its configuration, and at times is filled with sediment, and at times it's filled with ice. It's a dynamic exchange over a million year type time frequency. In the Gulf of Alaska, you get one of the highest sedimentation rates of any place on Earth, with sediment thicknesses of several hundred meters just during the last 10,000 years. And that's all the glacier sediment that was sitting on land, either on the glaciers or under the glaciers, or adjacent to the glacier margins, being flushed out by these cycles of glacier advance and retreat and melting.
Yes, I have a question. When you talk about the large percentage of the Earth's population
Yes.
living near the coasts or not too far inland, same condition of the infrastructure. What I always wonder about is the probable folly of people thinking we can build seawalls that are going to be large enough to somehow stave off that. How should we be thinking about these challenges beyond imagining building really taller and taller seawalls? Thank you.
That is a critical question. And that's one that's been debated for the last 100 years, depending on whether you own coastal property or you're paying taxes that are protecting somebody's coastal property. And it becomes a question, like in New Jersey, the cost of the infrastructure is less than the value of building the seawalls to protect it. So you have to decide, when enough is enough. And the federal government had been subsidizing the rebuilding of the barrier islands in the Carolinas up until a couple of years ago. And so there's a lot of consternation and concern as to what happens to this massive amount of infrastructure that needs to be protected as sea level, assuming the projections are correct that sea level will rise a quarter of a foot. That will have a dramatic impact in many places. Miami, highest elevation in the city of Miami is 4 feet above sea level. If you've been to New Orleans, you know you have to walk uphill to get to the Mississippi River because it's protected by these large levees. And the city itself is lower than that. The highest point in the New Orleans area is about 20 feet above sea level. If you look at the maps that show what the coast of the United States would look like with a 1 foot sea level rise, we lose dramatic amounts of coastal Virginia, even the Potomac River Basin, the tidal basin in Washington, D.C., gets inundated by high tides. And with a sea level rise of a foot, parts of downtown Washington, which originally were a swamp, will be underwater. So that's a real critical issue.
What do you suggest can be done other than the movement of people to higher ground? Or is there any other options like?
Well, that's a really good question because we've evolved from thinking that we could stop climate change to a philosophy, at least in the past administration, of what was called mitigation and adaptation. How do you minimize the impacts and how do you deal with the consequences? In a coastal environment, if you're going to keep your coastal barrier islands in existence, you've got to build protection. And that becomes extremely expensive. Can you relocate people? That's a really expensive proposition. And there's not available land in many places to move tens of thousands of people away from the coastline. So it depends on whether this is a government problem or a free market individual problem. And that has not been resolved. Yes, please.
Prompted by one of your photographs. Could you step back just a little bit? There's one that shows a fjord with a moraine right in the front of it. It's a very pronounced moraine that's fairly high. Keep going. Mostly water. Oh, that's not one. So as you're looking for it, I'll ask the question.
Okay.
It's really obvious that the location of that moraine sort of represented a point of maximum glaciation, at least for some at some
This
point
one?
in time. No, keep. Actually, that's a good one right there. Yeah, that
So
shows
here's the moraine.
a spit down on the that's partially grown over with vegetation.
Yes. That's the 1900 moraine.
Okay, so that represents a high or point of maximum glaciation right around 1900.
Yes.
Does that represent a local maximum point of glaciation at that temporal point?
In this particular case, it does. That may have been that location right here may have been the entire maximum extent for the Little Ice Age.
Mm-hmm. So there must be lots of evidence of that sort at various glaciers across Alaska and other places in the world.
No question.
And
there is.
Figuring out the things that happened in time, like the Mississippi and Ohio rivers is the point of maximum glaciation. Could you just talk about that subject a little bit?
Sure. One of the major tools that we use to try to understand the chronology of glacier events is called dendrochronology. If you core into trees that are growing on moraines and count the number of tree rings, and then throw in a fudge factor of how long it took for that tree to get established, you can get some idea of the age of that moraine. There's a location in southeastern Alaska around the Juneau ice field where a detailed study was done probably 60 years ago. And there you have the sequence of moraines where the ice would retreat, stabilize, build a ridge, then retreat for another decade, stabilize, build a ridge. And a botanist went out and cored all of these moraines, measured the ages of the trees, and was able to put together a complete sequence for 4 or 5 adjacent glaciers, documenting the chronology of post-1700 retreat. And so, similarly, when I told you those trees growing on the Malaspina Glacier stagnant ice were more than 200 years old, that's because we actually cored into the trees with something called a cypre core and counted the tree rings and documented what the age of those trees were. So dendrochronology is one tool. Radiocarbon dating for older glacier events, because typically you get organic material buried in the moraines. And that allows you to separate wood fragments or sometimes shells and date them. It gives you an idea when they were deposited. And then there are several other techniques that have to do with minerals like or chemical elements like beryllium, where on the surface of an exposed rock over time, there'll be weathering. And if you measure the crust of the rock and look at the chemical composition, you get some idea of how long it's been weathering in place. So if you take those types of tools and put them together, in many places you can get some kind of a chronology that allows you to understand the sequence of events. Hope that answers your question. Yes, please.
I'm curious what it felt like for you to come to these places and have that experience of seeing the ice retreat. But given the scale of the time scale in which you work, do you think of it sort of as this eternal change, or do you have an emotional response to it when you arrive and it's so vastly different?
In a lot of cases, we had no idea what we were going to find when we got there. And you have a photograph that was taken by somebody in the 1880s, and you have a general idea of the location. And you start saying, well, that peak is this one. And you say, oh my goodness, the ice can't even be seen from here anymore. And that's fairly traumatic when you think about the rapidity and the dynamic of the change. I started doing this repeat photography in 2000. And so I've been fortunate over the years to get to more than 200 different locations. So you become pretty jaded when you start realizing how fast and how dramatic the extent of changes can be. And you become very philosophical about it, that the Earth is dynamic and it's always going to change. And when I get really cynical, I realize that no matter what we as humans do to the Earth, there'll be some species of cockroach that'll love the end product. Please.
Something feeds these glaciers. I think it is snow. And you did mention that some glaciers actually are not receding, but they are actually growing. So when is it a matter of temperature, the temperature or climate being warmer, and when is the matter of precipitation being higher, and sort of what do we know about that?
Okay, so the ones that are advancing typically originate at higher elevations, close to a major water source, the Pacific Ocean. Many of them are in very steep valleys, so direct sunlight is not a major factor in causing ongoing melting. And typically they have disproportionately larger accumulation areas than they do ablation areas, where the ice accumulates as opposed to where it melts. Having said that, you can have two glaciers side by side that are doing totally different things. And it may be because of the morphology of the bed. It may be because of the fact that there's a slight difference in the amount of solar energy that reaches one versus the other. But typically the ones that are advancing are all within 100 kilometers of the Pacific Ocean, have high accumulation areas, typically are south flowing, but have narrower valleys. And some of them fluctuate. Some, such as the Hubbard Glacier, sat in the Pacific Ocean 1400 AD, retreated a distance of more than 30 miles, until the late 18th century and has re-advanced about 6 miles since then. There are a number of anomalous situations, and that's what confuses people. So if you're a climate denier and you're looking for evidence to say this isn't real, you can find all sorts of exceptions. Trying to understand the dynamics of the exceptions is complicated. Some of them don't have a logical answer. But overall, if you look at the volume of ice that has disappeared from the landmass in the last 1,000 years, it's extremely significant. And you compare what sea level is doing now versus what it did during the peak of the Little Ice Age, when the glaciers were significantly larger, we're seeing a rapid increase in sea level in many places, understanding that there are other factors that influence sea level as well. Any other questions?
Oh, we have one more question over here.
Sure.
You mentioned the Greenland glaciers as being the most probable ones that are causing the maximum sea level rise in the near future. I mean, compared to eastern Antarctica, which would be terrible. That'd be hundreds of feet, but that's not likely to happen soon. But the problem would be, could you expand on that a bit more? How fast is the Greenland glaciers going? Are they going to cause a 1 to 3 foot rise in the next 50 years, or is it only going to be 1 or half a foot or something?
Yeah. I showed you the IPCC figure. Actually, let's go back. Okay. So the IPCC says that 18 to 59 centimeters of sea level, 7 to 23 inches, depending on where you are on the Earth's surface, by 2100. Then they have a caveat. This does not include the catastrophic collapse of Antarctica. They didn't put in Greenland because at the time they made their prediction in 2013, Greenland wasn't being recognized as being as rapidly changing as it seems to be in the last 4 or 5 years. Yeah. So we just don't know is a simple answer. There is increased melting around the perimeter of Greenland. And even in the interior of Greenland, we're seeing meltwater on the surface that had never been observed. Certainly a decade ago was unknown. Whether this is indication that the rate of sea level change could be greater, stay tuned. That's all we can tell you. There's concern in Antarctica with the breakup of the ice shelves. The ice shelves serve as a brake. They keep the glaciers that are flowing from land into the oceans constrained. But if you remove the floating ice shelves, the glacier velocities can increase and the volume of transport can increase, contributing to an increase in sea level rise. The biggest fear, and it's not a high probability, is what's called the catastrophic collapse of the West Antarctic ice sheet. The bed becomes lubricated and the ice starts moving really rapidly, and thick sequences of glacier ice move into the ocean. People speculate about it, but it's not thought to be something to fear at the moment.
That'd be tens of feet.
Yes, it's tens of feet. So there's no evidence of a past collapse because the sediment record just doesn't preserve that kind of information. But as more and more models are being produced, some of the models show extreme types of failure that could accelerate the rate of melting by a significant fraction of an order of magnitude. Yes, please.
Right. I was very struck by a lot of your photos that showed the old trim lines and the terminal moraines at the end of the last mini ice age. You said in like 1750 for the Muir Glacier. I was wondering, is the glacier community of scientists up in Alaska doing any models about the prediction that came out a couple years ago based on the records from 1970s of the Stanford Solar Observatory? That study I'm sure you're familiar with, the UK and Russian scientists that predict about 97% accuracy based on some models of the sun that they came up with that were due for another Maunder minimum by about, 2022 and then 2030 or 2040, so that we might see another Maunder minimum like that one between 1650 and the 1700s.
Yeah, and that has to do with sunspot cycles and
Right, it has to do with the phase of the sun, and the whole deal is that the mathematical models say that we're due for one, so we could see a big advancing.
You could see
and I mean,
the rate of melting.
based on,
Yeah, I have to admit to you, that's not an area that I focus on, but I've read the predictions, and again, it's something that may prove to be true in the future. I don't know.
because I was very interested with one of the first question from the audience about those old fjords and channels underneath that big Piedmont glacier you've been studying, because if my background is more geology and then also using radar, airborne radar through triple canopy. So this is very interesting to me, this radar data with the ice penetrating from Mars. It could be that the geology is lining up with the little mini ice ages on those, and that we're just almost seeing, if we look at the whole picture, the stasis is, okay, the glaciers from way back here to here, and then you add in the tectonic. So that could explain why those channels weren't filled up with sediment.
Yes. There are a couple of places along the coast of Alaska where you can see fjords that were hundreds of meters below sea level, now sitting exposed 2,000 feet above sea level on the valley wall in places like Icy Bay, filled with massive younger sediment sequences. So in a tectonically active place like coastal Alaska, the current fjords have to be relatively young, meaning 1 or 2 million years old, because the fjords from 6 and 7 million years ago are now well exposed, well above sea level. But it's a dynamically reforming environment where the glaciers continue to erode, they form new fjords, tectonics pushes everything up. There are parts of Alaska that are going up, coastal Alaska going up several centimeters, good fraction of an inch a year. Yes, please.
I've been reading about as the glaciers melt, the land is rising under them because of the weight.
The isostatic readjustment, yes.
How significant is that?
Give you an example. Hudson's Bay in eastern Canada has risen something like 600 feet in the last 20,000 years, because there were several miles of ice that depressed the crust, and the ice melted away, and the isostatic readjustment continues to cause it to elevate. In the Little Ice Age time period, the best example is around Gustavus, Alaska, the mouth of Glacier Bay. There are periods of time when some of the rates approach 2 inches per year. And that is because the ice depressed the crust, the ice melted, and the crust is now readjusting. So that's a reality. There are many places along the east coast of the U.S. that are still rising after being depressed during the Pleistocene. So if you look at coastal Maine, you see there are numbers of glacial erosion features that were below sea level that are now exposed above sea level.
What is your opinion, or even your knowledge, of what does this mean for the Bay Area by 2100?
That's a good question, because the Bay Area has been so altered historically that almost all the shorelines are artificial. And with the Sacramento River Delta keeping sediment from flowing into the bay, you don't build new land that would allow you to compensate with rising sea level. But California is tectonically active and it's rising. So when you put all those together, I don't think there's going to be a significant amount of inundation in the Bay Area. Coyote Creek, the south end of the bay, keeps on getting flooded more and more frequently. But most of the San Francisco Peninsula is bedrock and is high and dry and will continue to be high and dry. So I don't think I'm giving you a good answer, but I don't envision there's going to be that substantial a change to Bay Area shorelines, with the exceptions of all of the low sediment areas around the southern perimeter of the bay.
Okay. Well, again, thank you all for your questions and for coming. Thank you, Anchor Bruce Molina. Thank you.
What you are telling me is Alaska